Right now, underneath the towns of San Bernardino, Riverside, and the Cajun Pass, two of Southern California's largest fault systems are sitting in a stress configuration that has never once been measured in 1,000 years of geologic record. No earthquake model built for this region has ever reconstructed a full millennium of stress history with this level of precision. No fault junction in California has ever been formally shown to behave like a gate that opens or closes depending on conditions. And no two adjacent fault segments here have ever been caught holding nearly matching stress levels at the exact moment those levels hit a historic peak. It is not a fault quietly waiting its turn. It is a gate sitting open at the highest pressure ever recorded on both sides of it. Stay with me, because this is a real peer-reviewed 2026 discovery, not speculation, and the part scientists are being careful not to say is almost more unsettling than the part they will say. If you're new here, this channel breaks down real current Earth science discoveries the moment the research drops. No disaster movie exaggeration, just the data. So if that sounds like your thing, hit subscribe. It costs nothing. Let us go back to the beginning. To understand why this new finding matters, you first need to understand what the San Andreas Fault actually is, because it is not a crack in the ground so much as a scar left by two entire tectonic plates grinding past each other. The Pacific Plate and the North American Plate meet along roughly 800 miles of California, sliding horizontally against one another at a pace of a couple of inches a year. Glacially slow by human standards, but geologically relentless. The trouble is that this motion is rarely smooth. Friction locks the two plates together along most of that boundary, and rather than sliding continuously, the rock deforms and stores energy, like a spring being wound tighter and tighter for years, decades, sometimes centuries, until the accumulated strain finally exceeds what the rock can hold, and the fault ruptures all at once. This is the basic physics known as elastic rebound theory, and it has held up remarkably well since seismologists first proposed it after studying the 1906 San Francisco earthquake, which killed thousands and leveled the city in under a minute of shaking. Southern California has its own defining event, the Fort Tejon earthquake of January 1857, an estimated magnitude 7.9 that tore through a long stretch of the southern San Andreas, and which, notably, is the last truly major rupture that section of the fault has produced. That's not a footnote. That quiet period, now approaching a century and 3/4, is precisely why California's earthquake scientists have spent decades warning that stress along the southern San Andreas has had an unusually long, unusually undisturbed run to keep building. None of this makes the San Andreas some kind of freak of nature either. Transform faults, like it exists all over the planet. The Alpine Fault in New Zealand, the North Anatolian Fault in Turkey, the Sauging Fault in Myanmar. Anywhere two plates slide past each other rather than colliding head-on or pulling apart. What makes the San Andreas system unusual is simply where it happens to run. Directly beneath one of the most populated, most economically vital stretches of coastline in the world, seismologists have spent the better part of a century building hazard models around this fault by studying it in pieces, treating the Mojave section, the Coachella section, the San Bernardino section, and the neighboring San Jacinto Fault as largely separate objects, each with its own rupture history and its own probability of failing on its own schedule. That approach wasn't naive. It reflected the honest limits of the data available. Paleoseismic trenches can only tell you so much about a single point on a fault line, and reconstructing how stress actually flows between multiple connected fault segments over centuries requires a level of computational modeling that simply didn't exist in a practical form until relatively recently. Here is the number that matters for everything that follows. Northeast of Los Angeles, the San Andreas Fault runs close enough to a second major fault, the San Jacinto, that the two systems nearly intersect at a geologically complex bottleneck called Cajun Pass. History shows this junction can behave two different ways. In December 1812, an earthquake near Wrightwood ruptured straight through the junction, breaking both the San Andreas and San Jacinto fault systems together as a single connected event. But when the much larger 1857 Fort Tejon earthquake tore through the same region 45 years later, it stopped cold right at Cajun Pass, leaving the San Jacinto Fault completely untouched. Same location, two totally different outcomes. For decades, seismologists had no reliable physics-based way to predict which of those two outcomes was more likely at any given moment, because building a model detailed enough to track how stress evolves across multiple interacting fault segments over centuries was, until recently, simply beyond available data and computing methods. That limitation wasn't a failure of the old science. It was an honest reflection of how hard this problem actually is, which is exactly what changed this year. In June 2026, a research team led by Dr. Lilian Burkhardt of the University of Bern, working with scientists from the University of Hawaii at Manoa, the U.S. Geological Survey's Earthquake Science Center, and Scripps Institution of Oceanography, published a study in the Journal of Geophysical Research. Solid Earth that did something no prior study had attempted at this resolution. They built a full 4 dimensional physics-based earthquake cycle model, tracking fault behavior in three-dimensional space and across time, and fed it a reconstructed 1,000-year earthquake history of the southern San Andreas and San Jacinto systems, pieced together from radiocarbon dating of buried fault scarps, tree ring records, and historical accounts of ground rupture stretching back centuries before modern instruments existed. Read that again. 1,000 years of earthquake behavior, reconstructed and simulated, tracking not just individual quakes, but how each one shifted the stress on every neighboring segment, how that stress slowly built during the quiet centuries in between, and how the deeper crust gradually relaxed after each major rupture. This is where it gets worse. According to the model's own output, stress across the region is now higher than at any other point in the entire 1,000-year window it examined. For years, that limitation meant Southern California's hazard maps could tell you which faults were dangerous in isolation, but not how they might behave in concert. A gap the new model was purpose-built to close. Now put a specific number to that. The model estimates that stress on the San Jacinto Fault's San Bernardino section has reached 3.6 megapascals, the highest value recorded anywhere in the full millennium of simulation, while the neighboring Mojave south section of the San Andreas Fault currently sits at 2.8 megapascals. On their own, those numbers mean little to anyone who isn't a structural geologist, so translate them to something you can picture. A single megapascal is roughly 10 times normal atmospheric pressure at sea level, the kind of pressure you'd feel about 100 meters underwater. 3.6 megapascals is the crustal equivalent of being crushed underwater more than a third of a kilometer deep. Except this pressure isn't pushing down from above, it's locked sideways into solid granite, with nowhere to go except through the fault itself. Here's where it gets worse though, and this is the actual headline the study is built around. It is not simply that both numbers are historically high, it's that they are close to each other. According to the research team, the deciding factor in whether a rupture stays confined to one fault or jumps the junction and tears through both isn't just how stressed a single fault is, it's how closely matched the stress levels are between the two adjacent systems. When one fault carries dramatically more stress than its neighbor, ruptures tend to stop at the junction the way Fort Tejon did in 1857. When the two systems carry similarly high stress at the same time, the junction behaves less like a wall and more like an open gate, which is precisely the configuration the researchers found sitting beneath Cajon Pass right now, in 2026, for the first time in the 1,000 years their model can see. This is not a fault that's simply overdue. This is a fault junction, whose current stress signature now statistically resembles the conditions that, historically, preceded joint multi-segment ruptures, not single, contained ones. Here is where this stops being an abstract number on a graph. Cajon Pass isn't an empty stretch of desert. It's one of the busiest infrastructure corridors in the entire American West, carrying Interstate 15, major freight and passenger rail lines, and high-voltage energy transmission that much of Southern California depends on, all funneled through a gap barely a few miles wide. A rupture confined to a single fault segment would already be a serious regional earthquake. A joint rupture crossing that gate, tearing through both the San Andreas and San Jacinto systems at once, would put an estimated magnitude, 7.4 to 7.8 event, directly beneath the greater Los Angeles area, San Bernardino, Riverside, and the Coachella Valley simultaneously. A stretch of Southern California that is home to more than 20 million people. This is not a hypothetical happening somewhere else. It is sitting directly beneath one of the most densely populated, most infrastructure-dependent corridors in the entire country. Think about what that actually means in practice. The freight lines that move a meaningful share of the goods entering the American West from the ports of Los Angeles and Long Beach thread directly through this pass, as do transmission corridors carrying power to homes far beyond Southern California itself. A rupture here wouldn't stay a regional story for long. To understand exactly why scientists are taking the joint rupture scenario seriously, rather than dismissing it as worst-case fear-mongering, you have to look at what happened on the other side of the world on March 28, 2025, along a fault that geologists have spent decades describing as the San Andreas' closest living relative. In the hours immediately after the shaking stopped, early damage reports out of Mandalay and Naypyidaw suggested a severe but geographically contained disaster, terrible for the communities directly along the fault, but roughly in line with what seismologists expected from a fault segment of that known length. That initial read turned out to be badly incomplete. That day, a magnitude 7.7 earthquake tore through central Myanmar along the Sagaing Fault, a long, mature, geometrically simple strike-slip fault, structurally almost identical in style to the San Andreas, just built from a different stretch of crust on the other side of the planet. The quake killed thousands of people and injured more than 11,000 more. But it was what happened after the shaking stopped. Once satellite radar and optical imagery let scientists actually map how far the ground had moved, that sent a genuine jolt through the seismology community. The rupture didn't stop where the models expected it to. It kept going and going. By the time Caltech researchers Solène Antoine and Jean-Philippe Avouac finished mapping the full extent of the break using satellite deformation data, the rupture stretched an almost unbelievable 510 kilometers. Imagine a single earthquake tearing a continuous scar in the ground, stretching from Los Angeles to well past Las Vegas, all in one event. With the ground on either side, sliding past itself by an average of 3.3 meters along the entire length. Worse still, portions of the rupture moved at what's called supershear velocity, faster than the seismic shear waves the earthquake itself was generating, exceeding 3 miles per second. A phenomenon so rare that seismologists get to study a clear, well-instrumented example only a handful of times in a career. The rupture broke through a segment that hadn't slipped since 1839, then kept propagating straight into neighboring segments that had already ruptured separately in 1930 and again in 2012, sections the old hazard models treated as independent, insulated compartments. They weren't. The stress from one segment's failure pushed straight into the next, and the next, in a single connected event that the standard scaling laws relating earthquake size to fault length and slip simply failed to predict. As the study's own authors put it, in an observation that has been quoted across earthquake science ever since, earthquakes never come back exactly the same way twice. That's the part that should sit with you. The Sauging Fault didn't do anything physically impossible. It did something the models said was unlikely on a fault built almost exactly like the one running through Cajun Pass. And the same Caltech team was explicit that this finding was a warning specifically aimed at how seismologists model the San Andreas. Because if a mature, geometrically simple strike-slip fault can blow past its expected segmentation once, there's no guarantee the boundaries drawn on California hazard maps are as solid as anyone assumed. None of this is happening in the dark either. Southern California sits under one of the densest earthquake monitoring networks on Earth, a mesh of GPS geodesy stations tracking millimeter-scale ground motion, seismometers feeding the state's Shake Alert early warning system, and satellite radar passes that let researchers like Burkhard's team spot deformation patterns invisible to any instrument on the ground. Here is what is happening right now in 2026, as scientists absorb both of these findings at once. The Burkhard team has been explicit and careful about what their study does and does not claim. Dr. Burkhard herself has stressed publicly that the research is not a prediction of when an earthquake will strike, only a clearer physics-based picture of how stressed the system currently is and which scenarios hazard planners should be preparing for. That distinction matters, and reputable scientists are holding the line on it even as public interest in the finding spikes. At the same time, other researchers studying the broader region haven't stayed quiet. Geologist Patrick Abbott, professor emeritus at San Diego State University, pointed in recent interviews to this year's earthquake disasters elsewhere in the world as a sobering comparison. The twin 7.2 and 7.5 magnitude earthquakes that struck Venezuela in June 2026 within seconds of each other, killing more than 3,300 people, and the catastrophic 2023 Turkey earthquake sequence, where a 7.8 followed a 7.3, and together killed more than 53,000. As real-world examples of what a big one followed almost immediately by a second major rupture can actually look like on the ground. Separately, this summer, researchers drilling sediment cores off the Oregon coast reported evidence, based on unusual landslide-triggered sediment layers, that a major Cascadia subduction zone earthquake in the Pacific Northwest could itself trigger a secondary rupture on the San Andreas Fault system far to the south, a possibility that, until this year, wasn't seriously modeled at all. None of these findings on their own tells us when. But stacked together in the same 12-month window, they represent one of the more significant updates to Southern California's seismic hazard picture in years, all converging on the same basic message. The assumptions baked into the old fault-by-fault hazard maps are being actively rewritten in real time. And there is one date, already locked into the calendar, that captures the strange gap between what scientists know and what the public is prepared for. On Thursday, October 15th, 2026, at exactly 10:15 in the morning local time, millions of Californians, schoolchildren, office workers, entire university campuses, will drop to the floor, take cover under a desk or table, and hold on for 1 minute, all at the same moment, as part of the Great California Shakeout, the largest earthquake preparedness drill on the planet. It is not a prediction. It is not tied to any forecast. It is an annual drill that has happened every October for over a decade. But this year, for the first time, it will happen with a peer-reviewed study on the record stating that the fault system beneath many of those same participants is sitting at its highest stress level in 1,000 years, at a junction now behaving, by the researcher's own description, like an open gate rather than a wall. Millions of people will practice for 1 minute what they'd do if the ground moved right then. Nobody knows if it will. That's not the point of the drill. But sit with the timing for a second anyway. A preparedness ritual that has run on the same clock for over a decade, arriving this particular year with a peer-reviewed number attached to it for the first time. Now, the honest part, because this story does not get to end with false certainty. The Burkhardt study's authors have been unusually direct about the limits of what a stress model can and cannot tell you. It can identify that a system is critically loaded, and it can identify the physical conditions that have historically preceded larger multi-fault ruptures. But it genuinely cannot tell you whether the next earthquake at Kajun Pass will be the confined single-fault kind, like 1857, or the connected both-faults kind, like 1812. Both remain live possibilities under the model's own findings, and the researchers have explicitly declined to call this a forecast of timing or size. Layered on top of that is the open question the Myanmar earthquake raised and never fully answered. Whether existing segmentation boundaries, the lines on the map that hazard models use to decide where one independent fault section ends and another begins, accurately describe how real ruptures actually propagate, or whether those boundaries are, in some cases, more a product of incomplete historical data than genuine physical barriers in the rock. Scientists don't have a settled answer to that yet, and to their credit, the Burkhardt team has not tried to paper over it. Their published discussion explicitly frames the earthquake gate behavior as probabilistic, describing conditions that make a joint rupture more or less favorable rather than certain. What most people are not seeing in the headlines built around this study is that critically stressed is a statement about present conditions, not a countdown clock, and any version of this story that turns it into one is going further than the actual peer-reviewed science does. Step back from Kajun Pass for a moment, and there's a larger pattern running underneath this entire story. For most of the 20th century, earthquake science treated individual fault segments almost like separate patients, each with its own chart, its own history, its own isolated risk profile. What the last 18 months of research, from Myanmar's super shear rupture to Burkhardt's 1,000-year Kajun Pass reconstruction, actually represents is a quiet paradigm shift. The recognition that faults don't fail in isolation, that stress moves between connected systems in ways that can only be seen once you're finally able to model the whole network together instead of one piece at a time. That shift didn't happen because the old scientists were careless. It happened because building a four-dimensional, 1,000-year, multi-fault stress model requires computing power, satellite geodesy, and reconstructed paleoseismic records that simply did not exist in a usable form even 15 years ago. This is what real scientific progress usually looks like from the inside. Not a single dramatic breakthrough, but the slow accumulation of better instruments and bigger data sets finally letting researchers ask a more honest, more complicated version of a question they've been asking all along. The uncomfortable part of that progress is that a more honest model doesn't always produce a more reassuring answer. Sometimes it just replaces one uncertainty with a sharper, better quantified one, which is, in its own way, exactly what has happened here. Think about what that means for how any of us are supposed to live with this information. A century ago, nobody living near Kajun Pass had any way of knowing what the rock beneath them was actually doing, and in some sense, that ignorance was its own kind of peace. Today, a research team on the other side of the planet can reconstruct 1,000 years of that same rock's behavior and tell you, with real physical numbers attached, exactly how tightly it's currently wound. And that knowledge doesn't come with an instruction manual for what to do with it beyond the same preparedness advice seismologists have been giving for decades. That's not a flaw in the science. It's simply what it looks like when a field matures faster than the culture around it knows how to absorb. There's an image worth holding on to after the numbers fade, somewhere beneath the traffic moving through Kajun Pass right now in rock nobody can see or touch. Two faults are pressed against each other at almost exactly matched tension. The way two hands might be locked together, palm to palm, each pushing with nearly identical force, neither one able to move first. Oh, so that's the actual physical picture behind the phrase earthquake gate. Not a door waiting to be kicked open by some outside force, but a balance held in absolute silence that has taken centuries to arrive at this particular configuration, and could, in principle, hold a while longer or not. Geologists have a quiet, almost startling way of talking about deep time that rarely makes it into headlines. The same rock now locked beneath the inland empire has done this before, dozens of times. Across 1,000 years this study can actually see, and thousands more it can't. It will keep doing it, in one form or another, long after every reader of this sentence is gone. The freeway traffic keeps moving through the pass regardless, headlights and taillights threading through a gap in the mountains that has already decided, more than once in the last 1,000 years, whether to let an earthquake pass quietly through or carry it all the way across. So here's everything, in one breath. The San Andreas and San Jacinto fault systems meet at a junction called Cajun Pass, which history shows can either stop a rupture cold, as it did in 1857, or let it cross straight through both faults at once, as it did in 1812. A new 2026 study led by Dr. Liliane Burkhardt, using 1,000 years of reconstructed earthquake data, found that stress at that junction has now reached its highest level in the entire millennium examined, with both adjacent fault segments carrying closely matched stress for the first time the model can see, a configuration historically associated with joint multifault ruptures rather than confined ones. A 2025 earthquake on Myanmar's Sagaing Fault, a close structural cousin of the San Andreas, ruptured over 500 kilometers in a single event, blowing past the segmentation boundaries older hazard models relied on. On October 15th, 2026, millions of Californians will practice the exact 1-minute drill designed for a moment like this, without knowing whether or when it will actually come. And the scientists behind the strongest new evidence are the first to say, on the record, that this is not a prediction, only a far clearer picture of exactly how loaded the gate really is. If this is the kind of research breakdown you want more of, real papers, real data, published the same year it's happening, subscribe and turn on notifications, because there's more coming out of this fault system before the year is over. Here's the question I actually want to know. If you lived in the Inland Empire right now, would you rather know exactly how stressed the fault beneath you is, even with no timeline attached? Or would you rather not know at all? Tell me in the comments. I rate every single one.